Today, we're going to pull back the curtain on the digital world and look at the invisible architecture that shapes, pretty much everything. The sounds you hear, the images you see. We're talking about the blueprints of digital signal processing, specifically what are called IR filter structures. It's the hidden engineering that makes all our tech just work. So have you ever looked at a really complex math equation and just thought, how on earth does that become a real-world tool? How does a bunch of symbols on a page turn into something that can clean up a noisy audio file or sharpen a blurry photo? Well, the answer is you've got to create a blueprint, a visual plan that an engineer can actually build. So here's our game plan for today. We're going to start with the basic idea of these digital blueprints. Then we'll look at a few specific designs, starting with the most basic one and then moving to a much smarter, more efficient version. We'll also see how you can build really complex filters using simple building blocks, and even what happens when you turn a design completely upside down. It's going to be fun. Okay, let's dive right in. Before you can build anything, I don't care if it's a house or a digital filter, you need a plan. And in the world of digital signals, that plan, that's the filter structure. So what is a filter structure? Well, it's pretty much exactly what it sounds like, an architectural blueprint. It's a diagram, sometimes called a signal flow graph, that takes a really dense mathematical equation and turns it into a clear step-by-step process. It shows you exactly where the signal goes in, what you do to it, and where the final processed signal comes out. It's the bridge that takes us from an abstract idea to something we can actually build. And just like with real architecture, there's not just one way to build something. Nope. There are several standard blueprints for these filters, and each one has its own quirks and advantages. We're going to focus on just a few of the big ones to really get a handle on the core ideas here. All right, let's start with the most straightforward design. It's called Direct Form 1. You can think of this as the first draft, the most literal, direct translation of the math into a diagram that you can actually follow. Okay, so at the heart of any filter is its transfer function. It looks like this. Now, I know, on its own, it can look pretty intimidating. It's just a jumble of letters and numbers. This tells us what the filter does, but it doesn't really show us how to build it. And for that, we need the blueprint. And this is how that crazy equation turns into a set of instructions anyone can follow. This is the direct form I structure. You can literally trace the path. The signal comes in over here, it flows through this whole network, gets multiplied by these B values, goes through some delay blocks, gets tweaked by the A values, and then the final result pops out on the other side. It's a perfect visual map of the math. So we've got a design that works. That's great. But in engineering, the very next question is always, can we do it better? Can we make it more efficient? And that's where our next blueprint, the Direct Form 2, comes into play. The key question here is all about optimization. Can we build the exact same filter, get the exact same result, but use fewer parts? In the world of digital filters, one of the most important parts is memory, which is represented by those little delay blocks. Those things are a crucial resource, so using fewer of them, well, that's a huge win. And check this out. Here they are, side by side. On the left, our first draft, Direct Form 1. On the right, the optimized Direct Form 2. They both do the exact same thing mathematically, but if you look close, you'll see that Direct Form 2 is super clever. It combines the delay elements into one central chain, basically cutting the number of memory blocks in half. Same result, fewer components. Now that is just smart design. Okay, so we've made our design more efficient, but what if we have a really complex filter to build? Well, instead of one giant, messy blueprint, what if we could build it from smaller, standardized pieces? Yeah, think of it like a building with Lego blocks. So this is the idea behind what's called the parallel form. We break down our big, complicated filter into smaller, simpler ones. The input signal gets sent to both of them at the same time, and their outputs are just added together at the end. It's kind of like having two specialists work on different parts of the same problem to get one combined result. The other way to do this is with the cascade form. Here, the blocks are all lined up in a row, kind of like an assembly line. The output from the first block becomes the input for the second block, and so on. Each stage does its part of the job before passing its result down the line. So why have two different modular ways to do this? Well, it all comes down to what you're trying to do. The parallel form, it's often used for things like band reject filters, where you want to stop a very specific frequency. The cascade form, on the other hand, is great for band pass filters, where you want to let a specific frequency through. Different tools for different jobs. All right, for our last big idea, we're going to try something that, well, it feels a little like magic. What happens if we take one of our original blueprints and just completely reverse the flow of the whole system? This gives us something called the transposed form. Now, there's actually a very clear recipe for how to do this. First, you reverse the direction of every single arrow in the diagram. Then, you swap the input and the output. And this is the key part. Any spot where signals were added together now becomes a spot where the signal splits, and any spot where it's split now becomes a spot where signals are added. And when you follow that recipe, this is what you get. The transposed direct form. It looks completely different from where we started, right? But the truly wild part is that mathematically, it produces the exact same result. It's just a powerful reminder that there can be totally different ways to get to the same goal. And that really gets us to the main takeaway of all this. One function can be achieved in many different forms, and that is the heart of elegant engineering. It's not just about finding one way that works, it's about understanding all the different paths you can take and knowing which one is the best for what you need, whether that's efficiency or modularity or something else entirely. So, I'll leave you with a little something to think about. If one single fundamental component, like a digital filter, has this much hidden design and architectural choice packed inside it, what other digital tools that we use every single day are way more complex and elegant than they appear on the surface? It really makes you look at the tech all around us in a whole new light.